So this is the part which we have learnt. Now we are going to look at the next part, that is monostable multivibrator. So let us try to get into this monostable multivibrator circuit. Right. So now in this part, let us try to see the monostable multivibrator circuit. So in yesterday's session, what we have discussed about multivibrator, same circuit we are going to look now. So the monostable multivibrator circuit, the Smith trigger circuit, yesterday what we have seen, the same circuit we try to take now, minus, plus. So at output we try to connect here one potential divider network and try to connect this to this circuit. So you are going to get it like this. Now, yesterday we have taken one capacitor like this and taken it to the ground. So this is a stable multivibrator circuit, yesterday what we have taken. Okay. Now to this stable multivibrator circuit, to make it work as a monostable multivibrator circuit, now we are going to take one diode in shunt with this capacitor. That is the difference which you find here. So this is diode D1 and we add one more diode to give trigger input to this circuit. So like this. So this is here nothing but trigger input we have here. So once you have this part, so this is a monostable multivibrator circuit. So what is the difference between a stable multivibrator circuit and monostable multivibrator circuit is, okay, you can get it here like this. Now, so in this case, the circuit has got additional diodes, D1 diode and D2 diode, okay, D2 diode. So you have here two diodes. D1 and D2. Okay. Now, so in this circuit, as the circuit now represents a stable multivibrator operation only most of the time here, but as it has got monostable name, it indicates here the characteristics of the circuit. That is, the circuit has one stable state, and one quasi-stable state. Quasi means temporary, okay, quasi-stable state, quasi-stable state. So the circuit has one stable state and one quasi-stable state and one quasi-stable state. So this is the what you call characteristic of this circuit, and the operation or functioning of the circuit will be like this. That is the function when trigger input is given. When trigger input is given, the circuit shifts its output from stable state to quasi-stable state, Okay, so the function, when trigger input is given, the circuit shifts its output from stable state to quasi-stable state and returns to stable state by itself after and returns to stable state after certain time period t, okay, where t will be equal to 0.69 RC. Okay, where t will be equal to 0.69 RC. Now you can understand for a stable, yesterday what we have seen, okay, for a stable what we have seen, T1, that is equal to capacitor charging, okay, charging of capacitor is given by 0.69 or you can take like this, T1 equal to charging of capacitor, T2 is equal to, okay, for a stable circuit, observe, T2 is equal to discharging of capacitor. So yesterday what we have taken, so total time period is equal to T1 plus T2. So you get, as the time period, charging and discharging time period of a stable multivibrator will be same. So you are going to get here 2 is equal to T. 2 is, both will be equal. So I write it as 2T1. So then it will become 2 into 0.69 RC, okay, RC, which will be equal to round about nearly 1.1, approximately it will be equal to 1.1 RC. So this is the time period of, okay, time period of a stable multivibrator. So yesterday we have taken only for charging part, okay. So the discharging part also you are supposed to take. So note down for the yesterday's circuit. Note for this circuit what you have written yesterday. Okay, for a stable circuit, charging we have done. Okay, charging time is equal to discharging time. Okay, then total time period should be equal to of one cycle. Total time period of one cycle will be equal to, okay, T1 plus T2. As both times are equal, you get here this as 2 into T1. So yesterday's answer 0.69 RC, you get it. So you will get here 1.1. This is for a stable. For monostable also you are going to get the same value, but you will not have charging, discharging two conditions here. Why? Because the circuit we try to understand the operation only for one pulse. Okay, so this stable multivibrator is nothing but a pulse generator. Once you try to press the button, that is once you give the trigger, okay, it will work as a pulse generator. So you need to understand for this it is like this. Okay, but for here, okay, because it is generating a square wave. So a monostable multivibrator will not generate a square wave here. Okay, it will generate a pulse. So this is also known as, this circuit is also known as pulse generator. Okay, pulse generator with time period T is equal to 0.69 RC. For this is for monostable. Okay, so for stable you are going to get it like this, and for monostable you are going to get it like this. Now we'll see how we'll get this part. How monostable will work, we'll try to see here. Okay, in the yesterday's part you note down this. Okay, otherwise both the time periods you will think that it will be same. Both the time periods are not same. Okay, there is a difference because here it is a square wave, here it is a pulse. So difference will be there between these two. Okay, now, so I am erasing this part. So one should understand the, I repeat here, this circuit functioning. The circuit has got one stable state and one quasi-stable state, that is temporary stable state. and function of this circuit is like this. When trigger input is given, the circuit shifts its output from stable state to quasi-stable state and returns to stable state by itself. Okay, no input is required. To shift from stable state to temporary stable state, we should give trigger. Okay, to return back to original stable state, we did not give any trigger. The circuit will come back to its by itself. How this circuit works, you can understand it like this. I am erasing this part. Now, so let me erase this. Now, let us try to see here how this circuit will work. Now, this is the circuit which we use in copy machine. Okay, so this is the circuit we are going to use it in copy machine. Suppose you observe the copy machine. Okay, you try to press the button. Okay, the moment you for pressing the button, you just put your finger on that and just press it and leave it. So for less than 1 second, you will just press the copy machine button and leave it. At that situation, what will happen is trigger is applied. So because of that, then immediately the output of this circuit will change and it will switch on the copy machine circuit, and immediately the coffee will be through the nozzle of the pipe. Okay, the coffee will be dumped into the cup. So once the coffee cup is filled, okay, so to fill the coffee cup, certain time period must be set. So before itself you should calculate, okay, how much time it will take for the cup to be filled. So based on that, you try to press the button, and once the coffee cup is filled, immediately after the time period, the circuit is going to return back to its stable state. Then once it returns to stable state, the circuit gets off. So therefore, immediately the nozzle will be closed, and there will be no further dumping of coffee from the nozzle. So the coffee coming from the cup, coffee falling into the cup from the nozzle will stop there. So you will be using for such kind of applications where we need permission for the circuit. Okay, the circuit needs permission from us, and once the permission is given, it will work, and once the job is finished, it will return back to its original state. Okay, then it did not have any permission. It returns because the job is done. It will return back to its original state, that is to the rest position. So that is how it works. So this is the circuit which we try to use. Now how it works, let us try to see here this part. Now once you try to give the power supply to this circuit, okay, it is not an oscillator, okay, it is not a square wave generator, it is a pulse generator. Output will be, okay, only a pulse generator. So once you try to provide here the power supply, okay, as I told you, once you provide here large amount of power supply here, because of the power supply large value, quickly this op-amp operating condition should be set such that it will go to saturation. So immediately the output of this circuit is at plus 15. Everybody can see here, this is plus 15. Now you can understand this as stable state. Okay, you can understand this as stable state. So now once the circuit is in stable state, at this situation, okay, now there is no change here. What will happen here is that set the values of resistors such that I'll have here 10 volts and I'll have here 5 volts. Now as I have here, now at this reference point, okay, V reference value will be equal to plus 5 volts. So now V reference value is here plus 5 volts. Okay, so because this is set at plus 15, the reference voltage based on the potential divider network, okay, based on the potential divider network will be set to here plus 5 volts. Okay, this is what you are going to get it. Now once this reference is set here, okay, once this reference is set here, now the next one what you have here is that here, okay, this, so the capacity, okay, put, but now what happens, everybody, the entire critical part is here. Try to observe. When the current comes from this, the diode, okay, very risky whenever you have a diode in shunt with any other device, because at any moment if the diode gets forward biased, the shunt element will not have any more voltage. Okay, its voltage will be fixed. Say now if it is a practical diode, under forward bias, a diode will act as, okay, closed circuit. Under closed circuit it offers very, very low resistance. Because of that reason, if you see here, now the entire current will go through this diode and reach the ground. Okay, therefore the capacitor also, because both of them are in shunt, capacitor will get opportunity only to charge only 0.7 volts. It cannot charge more than 0.7 volts. Okay, it cannot charge more than 0.7 volts. Okay, so this is the point you need to observe here. So once you have here the 0.7 volts here, and okay, as the diode has got 0.7, capacitor also will charge up to 0.7. Now at this situation, what will happen here is that this capacitor voltage, as it is fixed, you can see here voltage across the capacitor. You can see this branch. This branch is in now connected to the inverting input terminal. So voltage at this point also, now voltage across capacitor here also, VC which is there will be equal to 0.7 volts. Observe this point now. Now input is at 0.7 volts, minus terminal I consider it as input of comparator, and plus terminal I consider it as reference of the comparator. Okay, reference as comparator. So because of that reason, now this is at 0.7 volts. Okay, this is at 0.7 volts and this is at plus 5 volts. It means input is less than reference. Now the comparators always follow the same table. Vi less than V reference. Okay, the output will be okay equal to plus V sat, and Vi greater than V reference. Okay, V output is equal to minus V sat. Okay, V output is equal to minus V sat. Now Vi now greater equal to V reference, then V output equal to previous state. Okay, previous state. So this table always comparators follow only this table. Now, so based on this, now you can see here that input voltage what you have here. Okay, input voltage what you have here is at 0.7 and the reference voltage what you have here is at plus 5. So because these two are like this, okay, because these two are like this, what will happen is that this input is less than reference. Now you can see the comparator input less than V reference, V output equal to plus V sat, V output equal to plus V sat. So this is how you are going to get. So now already it is set to plus V sat, right? Now how long this circuit will continue this operation? Now as long as you try to give, okay, as long as you try to give the input here, what you are trying to observe is as long as you don't give any input here, the circuit is not going to change its state. Okay, it will try to remain in this state only. Why? Because whenever, as long as this output is at plus 15, never the capacitor will get opportunity to charge more than 0.7 because the diode is always forward biased. Okay, so from this point you can understand the logic of this circuit like this. As long as the diode is forward biased continuously, okay, is forward biased continuously, okay, you will never get any other voltage apart from this. Okay, you will never get any other voltage apart from this. Just a moment. Now look at this point here, that is plus 15 when you have here. Okay, now this diode will be always on. This diode will be always on. If the diode is always on, never you will get opportunity to, whenever the capacitor will get opportunity to charge up to more than 0.7. So as long as this input is at 0.7, the input will be less than reference only. As long as input is less than reference, then V output equal to, okay, plus V sat only. The V output will be equal to plus V sat only. It will not change. Okay, it will not change. So from this point, one can understand this, that, okay, the circuit, coffee machine, once it is on, okay, as long as you don't press button, it will not dump any coffee. Okay, it will be just waiting in standby position. That is how it works. Now at this situation, let us try to give trigger now. Okay, now trigger should be applied. So the first stage, what you need to do is trigger should be applied. The trigger voltage should be applied such that this diode will be on. So this is nothing but the trigger voltage. Okay, trigger voltage. Okay, so the trigger voltage should be applied here such that you need to remember this point. Note V trigger voltage. Okay, V trigger voltage should be, okay, V trigger voltage should be applied V trigger voltage should be applied such that, okay, V trigger voltage should be applied such that the V reference voltage, V reference should become, okay, Vt, that is Vt trigger voltage should be applied such that the reference voltage should become less than 0.7 volts. Okay, this is very, very important. Okay, one should observe this point very, very carefully. Okay, you need to understand here, okay, this point very carefully here. So this is very, very here important point. Then only this circuit will work, otherwise it will not work. So you need to take care here that this voltage, what you are giving at input, should be less than the 0.7 voltage. Now, so that is the reason I am giving here negative trigger. Okay, this is negative trigger I am giving, so that the diode will be on. If the diode is on, this voltage 5 volts will be reduced, and say that, okay, say for example, now say V reference is now 0.5 volts, because you have added this negative voltage to this. Now assume that diode is ideal. Okay, assume that diode is ideal. Okay, or you can consider practical also, it doesn't make difference. So if it is considered practical, you have to consider 0.7 volts here, otherwise you need not consider it. So this voltage, okay, this trigger voltage, when you try to apply this to the 0.7 volts, okay, 0.7 volts, then what happens here is that this plus voltage, okay, plus 5 will be added to this negative voltage. Net voltage should come down to 0.7 volt, 0.5 volts. Why we are doing like this? Because this is not going to change its output, change its state. This capacitor voltage is not going to change more than 0.7 volts. Why? Because as long as diode is forward biased, it will not change. Now at this moment, the moment you apply trigger, immediately reference voltage changes to 0.5, because this is not able to change, we change this only. The moment it becomes 0.5 volts, immediately what is going to happen? Immediately what is going to happen here is that input becomes greater than this reference. Now input is compared with this, okay, 0.7 volts, okay, is greater than 0.5 volts. You can see here, okay, on applying trigger, this voltage will become greater than this, because the trigger voltage made this reference voltage come down. Okay, now at this situation, what will happen here is that the output of this circuit is going to change from now plus 15 to minus 15. So this is quasi stable state. Okay, quasi stable state. Now it is changed to temporary state. So you can see the diagram now like this. Okay, you can see the diagram now like this. All of you carefully see how I am drawing this part. Now do not draw this diagram until I complete, because I make a change in intermediate level. So this is here V trigger, which is negative trigger pulse I am applying, so that voltage will become less than, okay, 0.7 volts. So now let us try to take here the output of this circuit like this. So as long as there is no trigger, you can see that output of this circuit is in plus Vsat. Output of the circuit will be in plus Vsat as long as there is no trigger. We output like this. The moment trigger is applied, immediately this is going to change from plus Vsat to minus Vsat. So you can observe here plus Vsat to minus Vsat. Okay, like this, from plus Vsat to minus Vsat. So once you get here to minus Vsat, it will continue to remain. How long it will remain? As I said, it will remain for only certain period of time t. Okay, it will remain there for certain period of time t. Okay, so it will try to remain like this. Now during this period what will happen is the capacitor gets opportunity to charge now. Why? Because if this output is at minus 15, all of you carefully look, if the output is at minus 15, okay, then this diode gets reverse biased. So you can see here now the diode is going to act as open circuit. Okay, diode is going to act as open circuit, and this capacitor what is there starts getting charged, okay, towards negative value. It starts charging towards negative supply. So now minus capacitor starts charging, okay, from this point. Now capacitor voltage, this is the voltage which you get across the capacitor. This voltage will start now changing from like this, minus 1, minus 2, minus 3, minus 4, minus 5. Okay, as this output is at minus 15, okay, and this voltage what you have will be shifted to minus volts because this has changed. Okay, this has changed. This will shift to minus pi. The trigger is applied only for short interval of time. So it will not keep 0.5 volts for very long. It will not keep 0.5 volts for long time because the coffee machine is pressed only for just fraction of second. You just press it and leave it. Okay, you just press it and leave it. You don't put your hand continuously on the button, isn't it? So you should understand that when the trigger is applied, then only that 5 volts will be made 0.5 volts. Once the trigger is removed, that is, trigger is applied for short interval of time. So you can see that this is the time period of the trigger pulse. Okay, this is the time period of the trigger pulse. Trigger pulse is applied only for short interval of time. So once trigger pulse is lost, okay, immediately what will happen? This reference voltage, the voltage at this point, at this node will become equal to VR2. VR2 is now minus 5. So therefore, as VR2 is minus 5, you are going to get this point minus 5. Now at this situation, now the capacitor started charging meanwhile because diode has become open circuit. Now minus 1, minus 2, minus 3, minus 4, minus 5 it has come. Now capacitor voltage will become minus 5.1. All of you carefully see, minus 5.1. Minus 5.1 is greater than minus 5. Carefully observe, minus 5.1 is greater than, minus 5.1 is less than, minus 5.1 is less than minus 5. As it is less than minus 5, you can see here when input is less than reference, V output should be at plus V sat. So immediately the circuit output what you see is going to shift from this point to this point, okay, like this, okay, like this it will shift. Okay, to this point. Now this will be the time period of the monostable multivibrator output. So this is the time period. So you can see here now this state and this state are nothing but stable states. Okay, stable states you have, and this part which you say is quasi stable state. Quasi stable state. Okay, or temporary stable state. So now this output, you have to drive this output of monostable, you should give it to a logic circuit. The logic circuit will take care of the rest of the functioning of the other circuits where you are using, such as it can be connected to a motor or it can be connected to any other circuit which will on the device or off the device, depends on logic how you try to use. Okay, because the output of any comparator is a digital output, it is not an analog output because it shifts between plus V sat and minus V sat. You have only, okay, one case there. So that is the reason you will find here, okay, that output here it is a quasi stable state. So once you have here, okay, like this, it will return back to this once the job is done. Okay, this time period you have to set it. How do you set this time period? By selecting proper value of RC of desired, okay, of proper value of RC, you can get your desired value of this pulse width. Okay, how much time, what you want. Okay, that is how the circuit is going to work. Now, so this is about the circuit operation, but you carefully see the output of circuit when it has to return back, it is decided by the capacitor. The output of circuit when it has to return back is decided by the capacitor. So you can see here that now I'll try to put here this also. Okay, in this case, everybody try to observe carefully what I am writing here. Okay, now the capacitor initially, okay, when the output is at plus V sat, all of you carefully observe, when the output is at plus V sat, the capacitor is charged. Okay, you can see here this is voltage across capacitor. So the capacitor will be charged up to 0.7 volts, not more than that. Okay, once trigger is applied, now the capacitor gets opportunity to charge, okay, for less value to the output voltage minus VCC. So at this situation, now once the capacitor starts charging, you can see here it will charge up to here. What is this voltage? This is nothing but minus V reference. It means capacitor will charge up to minus V reference. The capacitor has desired to charge up to minus 15, but it will not get opportunity because the moment capacitor voltage becomes minus 5.5, then input is less than reference, so the output has to shift. So that is the reason capacitor will get opportunity to charge only up to this point. Once the job is done, okay, because of the connection system which you have done, okay, the capacitor starts discharging quickly. It doesn't take much time, okay, it will be because the discharging path for the capacitor is placed like this. That is, once again, when the capacitor gets positive voltage, diode is on. Now you will get current from this point, and you also get current from this capacitor, which it has stored. Whatever negative charge it has stored, it has to discharge through that path. So when it discharges, once again, because diode offers very low resistance, quick discharging will take place, and once again capacitor will charge up to 0.7 and remain here only. It will charge up to 0.7 and remain at this point only. It cannot go more than this. Okay, it will charge up to 0.7. So it is the capacitor voltage which will change the state of the circuit. Okay, this is the operation of the monostable multivibrator circuit we have. Okay, now so let us try to see here. Now, so understand this waveforms. Once again, I put it here very clearly. This is one of the very important circuits we have. Once you give trigger, before you give trigger, the circuit will be in stable state. That is, output is in plus Vsat. When it is in plus Vsat, okay, the capacitor diode will be on, D1 will be on. Therefore, capacitor will not get opportunity to charge more than 0.7 volts. As it does not get opportunity to charge more than 0.7 volts, therefore what will happen here is that the capacitor voltage will be clamped to 0.7 volts forever, okay, as long as diode is on, D1 is on. At this situation, the input terminal at this negative terminal, voltage will be fixed to 0.7 and this will be fixed to plus 5 volts. At that situation, input will be always less than reference, so output remains in plus Vsat. You can see here. The moment I give trigger, okay, trigger should be given only for short interval of time. You should not increase. If you continuously put the hand on the copy machine button continuously, then what will happen is the trigger pulse width will increase. Then you have to remove the cup and put a bucket over there because the machine will never stop. Continuously it will be pouring. So you need to understand this point very carefully. You need to just give trigger for short interval. The moment you press, immediately this voltage will become less than 0.5 volts, that is less than 0.7 is fixed here. So say for example, we are saying just now, say it is 0.5. For example, I have taken it. You can go any voltage less than 0.7 volts. Once you come down any voltage less than 0.7 volts, then immediately, okay, you will observe here that the input will become greater than reference and output will shift to minus Vsat. And when it is minus Vsat, first D1 diode will get reverse biased. Therefore, capacitor starts charging towards negative. And when it is charging towards negative, at some point minus 5.1 volts when it reaches, again this reference has also changed to minus 5. Therefore, you will observe here that minus 5.1 volt, what you have here, okay, is less than reference voltage. Therefore, output shifts to plus Vsat. It comes back. Okay, so the moment when capacitor takes charging, you can see here from this point to minus 5.1. Okay, how much time the capacitor takes to charge up to negative reference, based on that the time period of the circuit will be decided. Pulse width will be decided based on that. So this is the operation of a monostable multivibrator circuit. Now let us try to see. I am erasing this part. Now you can see here the expression for time period. So for that we have to take the standard RC network equation. V voltage across capacitor is equal to V final yesterday's circuit, okay, V initial minus V final into e power minus t by RC. So this is what you have. So here the capacitor is capacitor cannot charge to plus Vsat or plus V reference. Why? Because always diode is limiting it to 0.7 volts. So you will not get plus Vsat. It means the capacitor will charge only up to negative reference minus V reference here. Okay, minus V reference. You can take it or LTP also. Now, so what you have here is that this point, now the capacitor V final voltage, the capacitor gets, if opportunity is provided, then the capacitor will charge up to, okay, minus Vsat plus V initial. The capacitor voltage initially is fixed to 0.7 volts. So this is voltage across diode D1, and V final is again here minus Vsat here. Okay, minus Vsat here. E power t by RC. This is what I am going to get. Now here in the same manner yesterday's function, you need to shift this point this side. So minus V reference here, okay, minus Vsat you are going to get, okay, is equal to VD1 minus of minus Vsat into e power minus t by RC. Okay, this is what is the value you are going to get now from this. Okay, like this. Now shift that e power minus t by RC, you are going to get, here you are going to get this as VD1, okay, sorry, minus V reference minus Vsat, okay, whole divided by VD1 minus of minus Vsat. Okay, this is the point you are going to get. Now copy this diagram. I am going to erase this. Copy the diagram quickly. I am sorry, when you turn this side, this is plus here, this is plus here. When you bring this minus Vsat this side, it is plus here, and here it is plus here. You have. Fine. Now let us try to write these values of this source values. Now here minus V reference I have here. Now let me take here log function on both sides. Now taking log on both sides. Taking log on both sides, I get minus t by RC is equal to ln of here, okay, Vsat minus V reference, okay, whole divided by, okay, VD1, okay, plus Vsat. You can take it here. Now from this point, let us try to take here this point. Now minus t by RC. Send this minus this side. Then I am going to get this equation like this. T is equal to minus RC, okay, ln minus RC ln Vsat minus V reference divided by VD1 plus Vsat. Okay. Now this minus, if you shift it here, then here you are going to get here RC. Observe this point here, minus is referred. So take this minus here, then it becomes x inverse. I write it VD1 plus Vsat, okay, whole divided by Vsat minus, okay, what is negative reference? Okay, that also will write. So negative reference is minus Vsat R2 divided by R1 plus R2. Okay, this is what is the what do you call negative V reference you have. So now I am going to get like this, RC into Ln. This will be 0.7 volts, okay, plus Vsat, okay, whole divided by Vsat minus Vsat to R2 divided by R1 plus R2. So now I am going to get it like this, okay. Here 0.7 is much less than Vsat value, so neglect 0.7 volts. So then you are going to get RC into Ln. I am going to get 1 by 1 minus, cancel all Vsat. I am going to get R2 divided by R1 plus R2. So here I am going to get this as RC Ln R1 plus R2 whole divided by R1, right. Now if you try to say here RC Ln, this value, if you try to take here, now you are going to get this here 1 plus R2 divided by R1, okay. You are supposed to get it like this. So this is the point you get when you try to equate this time period, okay, t is equal to this, okay. You are supposed to get here t is equal to 0.69 RC when you equate the values of R1 and R2 equal, R1 equal to R2. So you are going to get time period of this pulse width will be t is equal to 0.69 RC. So this is the point which you are going to get it. Now so let us take break and come back. Resistance oscillator. Suppose you try to take a UJT and connect one capacitor to the UJT, okay, in shunt to its B1 terminal, then that circuit is going to work like a negative resistance oscillator, okay. So that is what you have. What do you mean by that? In sense, when you try to increase voltage, current should increase. If current is decreasing, and as decrease in current what you have, okay, should come down, okay, such that that value output of that circuit should become, okay, a periodic signal, then we consider that to be as a negative resistance oscillator. Okay, SCR will function and UJT in combination with the RC network across its shunt, then it will work. Okay, these two it will work. Next, Disha from Jammu. Sir, what kind of questions are generally asked on monostable multivibrator? He'll ask you what will be the time period and what will be the trigger frequency I should give such that I should get so and so time period. It is understood that as time period of this trigger, what I have drawn earlier, is lesser than the time period of the pulse, obviously trigger pulse frequency will be more. So then the monostable multivibrator also can act as a square wave generator if you are continuously giving the inputs to the trigger. Okay, so for such kind of questions you will get. Okay, but here you don't get frequency unless until trigger is continuous, because this gives only once the output. Once you press trigger, only one time you get the output. Second time if you want the output, it will not change. You have to give trigger once again. So apart from this, you don't find anything. Based on RC network, what will be the time period pulse width? Okay, if I want to change the pulse width, what should I do? Or for a given circuit, what will be the voltage, capacitor voltage at which the trigger will occur? Like that also, that is the output will change its state from quasi-stable state to stable state. Like these questions you will be getting it. Next, Abhishek, 1 microsecond pulse can converted into 1 millisecond pulse by using monostable multivibrator. 1 microsecond pulse can be converted into 1 millisecond pulse. What do you mean by that in sense? 1 microsecond pulse is for trigger and 1 millisecond pulse is for the output of monostable multivibrator. So that is what is the meaning. But you should not understand that 1 microsecond has become 1 millisecond, okay, just by the circuit. The circuit will not do that. What you need to understand is trigger is less time period and the time period of the output of the circuit will be large. Just now as I was telling. That is the meaning of that statement what you have written, Abhishek. Both do not belong to the output of monostable multivibrator. Do not assume that. That is wrong. Next. Anvesha, Mumbai. Sir, what kind of questions can we expect from multivibrator topic? Numericals based on time period can only come. Numerical based on time period can only come in. Yes, what you have written, that is right. Just now I have answered, Anvesha. Ashutosh from Bilai. Sir, if we use a very small value of capacitor in shunt with the resistor in combination and connect it to the input of monostable multivibrator, then I guess no matter how long we press the switch continue as we generate the spikes like waveform in such case. Is it possible or not? Right. So if you try to put the time period of that is capacitor very low value, what happens is it will get saturated, okay, very quickly. So it will stick to 0.7 volts. Okay, that is the point. Then what happens is the output of this pulse what you are getting, that pulse time period will be decreased. That is what is going to happen. Now to get a spikes what you are trying to mention, okay, now you should not take the combination of this and that. Okay, the spike is possible when you try to discharge the capacitor very fast. But where is the chance for the capacitor to discharge? The only way is through the diode. That is, if diode is on, then it will charge, its voltage will be fixed to 0.7. When diode is off, then only the capacitor will charge. So it means it is not possible how the way what you have thought, because there is no discharging path for the capacitor apart from diode. That is the point you need to remember. So you will not get that spikes. Only it is in differentiator circuit what we have studied you get, because of the design and the discharge path we provide for the capacitor. So here we don't do that. Next. But one thing I can comment is that if you put capacitor very short, you will get less the pulse width. That is what you are going to get. Next, Ashutosh from Bilai. Sir, always this 0.69 is there as constant term. Is it mean that always multivibrator universally this would work like that? I am sorry, Ashutosh, it is not so. You try to take R1 equal to R2, then this will become 1. 1 plus 1 is 2. Log 2 value is 0.69. Previously also, because we have RC, there also we got log 2 value 0.69. But it is only charging period we got what you call 0.69. When you consider total cycle in a stable multivibrator, that is you have to take charging plus discharging. Then there I get T is equal to 1.1 RC, 2 into 0.69. So it is not something like constant there. Okay, do not misunderstand that part. When I try to equate this, then only I'll get this. Otherwise, I'm not going to get it. Select R2 100 and select this 10. Then 10 divided by 100 divided by 10, then I am going to get log 11. Then this will not be here, okay, equal to that point. It means if we give control only to RC, then we cannot change these parameters because capacitors are not available of your choice. Okay, they are not available in wide range. They are available in limited range. That is the reason we try to use the resistor help also in the circuit and try to adjust the time period. Okay, that is the point. That's the reason I have given. Otherwise, if RC is only very important, we have taken only this formula. We would not struggle all this with this. You should understand from this expression that apart from RC, resistors also take control. So 0.69 is not constant. As we are taking this point in any textbooks or the example always, that is the reason you are getting points. But you should not fix to that value. Next, Dinesh from Mumbai. What is total transconductance GM of two transistors connected in Darlington pair? Okay, because transconductance you are calculating there. Okay, it is out of topic, Dinesh. Okay, but I try to put it in brief. Let me put it in brief. Okay, the point here is that Darlington pair is nothing but cascaded CC configurations. So you are going to get, when I come to that point, I'll try to tell you. Okay, it is like this. It means output of this emitter, this is CC configuration. Output of this will become input to this. And again you will get here IE2. Are you getting it? So write down the relation between IE and IB here and IE and IB here. Then you will get ratio of this current to what voltage you are giving here you should take. Then if you take this becomes transconductance here. Put the values IE equal to, okay, IC is beta times IB1. IB1 will be equal to IE1 and IE1 will be equal to beta into IB1. So you try to put, then you will get output current. And once you get the output current, then find out what is input voltage. Take the ratio of these two, you are going to get it here. Okay, you will get a formula over there. Now I cannot discuss more than this. Next. Now look here, next one, that is Dinesh from Mumbai. A resistance R equal to 1 ohm in series with capacitor with resistance 1 ohm. R is in series with capacitor with resistance 1 ohm. Input to this circuit at resistance end is 1 volt AC. What is output voltage across capacitor? Okay, this first the question is not clear because a resistance R equal to 1 ohm is in series with capacitor. Okay, with reactance 1 ohm. Okay, it is not resistance, reactance. Okay, fine. Resistance 1 ohm. With reactance means that is also series. If I understand that, that is also series. If it is so, okay, you are supposed to calculate. Now, the total, what do you call, reactance or the total impedance when you try to take, it will be 2 ohms because based on what you have provided there, what I understand. Okay, so total you are supposed to take R plus, real part of that reactance, you have to add it to the resistance. And whatever reactance that is imaginary part is there, that also you have to take. And add minus JXE. That is the point. Now to this the input to this circuit at resistance end is 1 volt. So at resistance end is 1 volt means, so then definitely 1 ampere must be the current. So what will the output across the capacitor? So you can directly take the voltage current voltage across capacitor is equal to VC equal to voltage across capacitor VC equal to minus 1 by integral of VI into dt. Okay, so you are supposed to apply that formula C into dVC by dt for current, output current, and for voltage, okay, you are supposed to take 1 by C into integral of VI dt. So for the current sake, so you try to apply the voltage formula and current formula. Okay, for the capacitor you are going to get it. Current formula is this: I is equal to current through capacitor C dVC by dt, and voltage across capacitor is 1 by C into integral of I of t dt. So these are the formulas. So as I told you, current is 1 ampere. Put it here. Put the capacitor value. If you want current, you get current. If you want voltage, okay, you will try to select them, okay, for using these circuits, what we are going to study. So now stable and monostable, what you have seen just now using op-amp, okay, these are time-based application, but here due to offset problems or due to some error voltages, okay, they may not produce accurate outputs. So that is the reason they have observed these time-based applications and have developed a circuit called 555 timer. Okay, 555 timer. So let us try to see now. Here, this is the circuit. 555 timer. Okay, 555 timer circuit. So one can understand like this: the 555 timer circuit is nothing but a comparator device once again, but it can give us flexibility in operations of the circuit. It can give us flexibility in operations of the circuit, such that whatever time you want, you can set it and get the output of the circuit function based on this. It can do multiple jobs. All operations what we have studied now, those operations can be done with this 555 timer also. You would get better output here than the previous one. Now let us try to see here how it works. Now try to see this. Let us see here first the pin diagram of 555 timer. Pin diagram of 555 timer. 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 pins, and this is the 555 timer. Pin number 1 is considered to be ground, and pin number 2 here, and pin number 3 you try to observe the trigger is given to this. The trigger, this is voltage trigger you give to pin number 2, and output of the 555 timer you take it from pin number 3, and 4, pin number 4 is reset, and pin number 5 here we call this pin number 5 control voltage. Now pin number 6 is here given threshold voltage. Pin number 7 here, this is called discharge pin, discharge pin, and pin number 8 is plus VCC what we provide, So this is the pin configuration. Now let us try to understand here this pin configuration properly. What do you understand by this pin configuration? Everybody try to see here, that now when you observe this ground pin, so when you try to do the experiments in the lab, why most of the students get proper results? Because you try to ground it to the the ground part of the breadboard or any other provision you have. But you should not connect like this when you are doing with integrated circuits. If the pin or integrated circuit or IC is given a pin called ground terminal, you have to bring all voltages to the ground point. That is pin number 1 in this case. Then only you are going to get output properly. Otherwise that outputs you will not be getting expected outputs. You will be locked somewhere, or you will get distorted output or something else. So you should remember that is the importance of the pin. What voltage you give trigger, the trigger will have 2 points. One is potential, one is at 0 potential, one is at higher potential, or lower and higher. The lower potential point you should bring it and connect it to ground. So the output also you should take it among this point. And reset pin, you will try to provide voltage. Here also you will have 2 points. One pin must be connected. Like that, from every pin you should return back to pin number 1. That is the importance. Then you are going to get proper results. Now next, observe here V trigger. This is the trigger voltage what you are going to get. Trigger pin just now what we have observed for monostable. Like that, here also we give trigger. That you have to provide it with the help of pin number 2. Output you take it from the pin number 3. Reset. When you start any experiment, it is always better to reset the 555 timer. Why? Because it has got a flip-flop. Flip-flop is a memory element. Once it stores data, unless until you give the input to the flip-flop, it will not change its output state. That is the reason you have to put this reset pin. You have to reset the output of the circuit before you do the experiments. Next, control voltage. So if you want to change the what you call output voltage based on your requirement, if you want to make any changes, then you try to use this pin number 5. Okay, next one here we have is threshold voltage. Okay, what do you mean by threshold? Means at which level of voltage you want to change the output. You want the output to change at 3 volts, you want to change the output at 5 volts or at 8 volts. If you want to decide like that, that voltage will be decided here as threshold voltage. Now discharge pin. Here, when we try to use this as a multivibrator circuits, there will be a capacitor. You have to allow that capacitor to discharge. Otherwise, the circuit output will be always constant. It will never come out. If you put a LED or whatever it is, they keep on glowing. They will not blink. Okay, so this is the point. So for that, you have to allow the capacitor to charge and allow the capacitor to discharge. So for that, provision must be there. So that provision is nothing but discharge pin. Okay, 7 here, and 8 is nothing but power supply here we have. So one can observe this here, simplified timer circuit like this. Now this is about pin diagram we have. Now block diagram of simplified timer, let us see here. Everybody try to see the block diagram. While I am drawing, try to observe first, later you can copy. Okay, block diagram. Block diagram of IC 555, very important. Okay, now try to see here for this function. Now first I am taking here the resistance. So please do observe how I am taking the resistance. It's very important. Now I ground it here. As I am grounding, this becomes pin number 1. I provide here the VCC power supply here. So this is plus VCC. So this will become pin number 8. Okay. Now these resistors are selected of equal value 5K, 5K, 5K. That is the reason it is called as 555 timer. Okay, 5K, 5K, 5K. Now this circuit has got 2 comparators. Okay, everybody carefully observe. This circuit has got 2 comparators like this. Now minus here, plus here. Now the output of this circuit, I connect it here. Do not write until I complete. I'll change the positions. Based on the explanation, I'll be changing. Let me complete it, then you can copy. Now the output of this comparators is a digital output. So I connect this to a flip-flop here, Q bar, and I have here this and Q bar here like this. Okay, now this and this. So when you have here, all of you carefully see the output. I am taking it across Q bar here. Okay, now I have here this transistor connected to this Q output. Now the collector of this is connected to this transistor. Okay, one can see here like this. Now this is called discharge transistor QD, and you have the output here. This is the final output what you are going to get from this Q bar. So to reset this flip-flop, we need one transistor or a switch. So this I am going to take it here as pin number 4. Okay, reset. Okay, reset pin number 4, and this is pin number 3 here. I have pin number 3 here. I have. Now this is reset pin number 3. Pin number 1 I have here. Now here So as you observe, till now we have taken comparator like this, minus terminal as input and plus terminal as reference in comparators, right? So this comparator what you are seeing is also taken like this. Let this comparator be here A2. Okay, let this comparator be here A2. Now carefully observe everybody, the trigger input I try to give it to this. So this I consider here pin number 2. Okay, pin number 2 trigger input. And this point which is their reference, I connect it to this resistance. Because resistance is constant, VCC is constant, then the reference voltage also will be constant. And this voltage, what you observe here, is distributed equally among these three. Therefore, whenever you cross one resistor, you will have 1/3 voltage drop. Okay, so I'll have here 1/3 voltage, or 2/3 VCC. 1/3 is lost. If I cross this also, left out voltage here will be 1/3 VCC. So the voltage across this will be equal to, voltage across 5K will be equal to 1/3 VCC. Okay, voltage across this. Now voltage across this point, if you try to see here, okay, now what we are going to get is, carefully observe everybody, I am fixing this 2 point to this. So I will get here, voltage across this resistor will be equal to voltage across this 5K, second 5K, okay, will be equal to here 2/3 VCC, okay, 2/3 VCC, voltage at this point, voltage across this, okay, everybody. Now, so the plus terminal you have given an extended terminal up to this point. Now, previously, this is comparator, this is also, both are comparators only, that is A1 and A2. But what is the small difference which you find is, here this will work, here you will observe the things in normal way, that is input given to inverting and reference given to plus. But here it is not like that, input will be given to plus terminal and minus terminal which is there will be given reference. Okay, that is how we should understand. So you can understand the circuit. Comparator is not going to change its table functionality. It will work in the same manner. Okay, comparator will work according to the table only, what we have written earlier. But what the story here is, here the negative terminal, it means you can understand like this, input is kept constant and reference only is varied. You can understand like that. Okay, instead of taking the previous part. So both these are comparators and they work on the same principle what we have studied like this. V input less than V reference, okay, then V output will be at plus V sat, and V input greater than V reference, then V output is equal to minus V sat. Okay, like this it will work. They are fixed, no change. So A1 and A2 work according to above table. Okay, both will work. For A1 only, you should remember that plus is not given reference, plus is given changing reference you can say, and minus is not given input, you can say constant input is given. Like that you can remember. Okay, fine. Keep it like this. Why so? You will understand once I start giving the explanation. Now, so this is here pin number 6. Okay, we have here pin number 6 and this is here pin number 5. What you have here, most of the times unless application demands, we don't generally touch pin number 5 control voltage. It will be fixed. Now, this is here pin number 7. So I have here pin 1, okay, pin 2, pin 3, 4 and 5, 6, 7, 8. So 8 pins are filled. This is the block diagram of the, okay, 555 timer. Now you can copy this part. Now let us see here. This 555 timer circuit is going to work like a monostable multivibrator. It is going to work like a stable multivibrator. So for both of these operations, we need to connect external terminal. Okay, let us try to see here. Now this is the inside block diagram. Okay, when you want to make this circuit work as monostable, okay, multivibrator, then for your understanding, I am writing this point like this. Okay, in case of monostable multivibrator, this is pin number 8, pin number 7. Okay, you have here pin number 6. Okay, pin number 2. So here trigger will be given. Okay, pin number 6 and 7. What you have here? Okay, like this. And pin number 8 you have. So pin number 7 and 6 are shorted, and the pin number 6 here is connected to one capacitor and grounded, one R and one C. Okay, so you have here pin 2 for trigger, right, and this is connected to VCC. So from pin 3 we are going to take output. The pins are rearranged for your understanding. The pin numbers here I have rearranged for your understanding to have simple diagram. Okay, but the pins are not going to change. Don't understand it like this. Here I have rearranged only for your understanding. Now R here, C here. Okay, now this is how the 555 timer circuit will be connected in the lab from external part. So let us try to take here the same thing in this way. Now I have here 6, I have here 2, and I have here 7. Now from this 8, pin number 8, I am going to take the output. Now let us try to see. First what you need to do is that is short this pin 7 and 6. So once you short it, and I have here one capacitor, I connected the capacitor to this point. So this is capacitor and this is here resistor. Okay, now I can have it like this. So now once I have this circuit R here and C here, everyone can see here this point. Okay, now as usual we have to reset first. Now this is here monostable multivibrator circuit. Monostable multivibrator circuit. Okay, monostable multivibrator circuit. So for this, let us try to start here. Once we have connected R and C. Now initially the op amp has to be, that is the flip flop must be set to 0. Now you need to follow here the truth table of the flip flop. So the truth table of the flip flop here is given like this. Now 0 0 0 1 1 0 1 1 is eliminated. Okay, so if the outputs will be like this, Q Qn bar, that is you will get here Qn Qn bar. Okay, and here you will get 0 1. V output plus Vsat. Plus Vsat I will consider it as 1. Vi greater than V reference, then V output equal to minus Vsat. Then I consider this as 0. This you need to remember. Okay, fine. Now let us here try to start this point. Now let us start the operation. First, once the circuit is given to you, now reset this pin number using the pin number 4. Okay, reset this using pin number 4. So once you reset it, you should reset it in such a way that now this Q become 1 and this becomes 0. Reset values. Okay, here this value is 1 and this is 0. Okay, these are reset values. Now the output of the circuit I am trying to draw here. Because Q is 0, you will find that there is no output, 0 here. The output waveform. Okay, it is 0 here. Right, fine. So I have reset it like this using this pin. Okay, I will reset the output Q1, Q0. If I reset this as 1, then what will happen? You see here, everybody. If I reset this as 1, then this transistor voltage will become high. So what VCC you give here, that in order to make this flip flop also work, you have to give VCC for this also. Internal connection will be there. Internal connection will be there. Okay, now because of that internal connection, what you have here, carefully observe. Okay, excuse me. So what will happen here is that here also you will have VCC. Output 1 means here also you will get high voltage only. Here also you are going to get high voltage only. Say for example, you have given here VCC equal to 9 volts. Observe here VCC you have given 9 volts. Then here 2/3 VCC will become 6 volts. And this 1/3 VCC will become 3 volts like this. 1/3 VCC will become 3 volts. Example. So I fix here this as 3 volts and I fix this here, okay, as 6 volts. Observe here. So voltage here, that is equal to Okay, voltage at this point will be equal to 2/3 VCC, that I am writing it here as 6 volts because I have taken here 9 volts. Now like this, when it is there, everybody try to observe, we set a value 1 and 0. Okay, based on that what happens is, carefully observe the transistor, resistor and capacitor. Okay, leave about the pins. Now I have here the transistor. It means this capacitor is in shunt with the transistor. Carefully observe. The capacitor is in shunt with the transistor. As it is in shunt with the transistor, when I provide here 1 volt, 1, okay, 1, output 1 means I am providing high voltage, 9 volts. So from here I am giving 9 volts. So there is a drop of 1 volt here, then I will get here 8 volts. Carefully observe, I will get here 8 volts. Because this is 9 minus 8, okay, 9 minus 8 you can say. Okay, from this point to this point you are supposed to take here 9. Okay, so I am supposed to write here like this, 9 minus 8 equal to 1 volt. Okay, this junction is forward biased. 9 minus 0 I write equal to 9 volts. So this junction is also forward biased. Both are forward biased. The transistor is in saturation. Under saturation condition, the transistor is going to work as a closed switch. Okay, or a short circuit you can say. So then this transistor which is there will act as a short circuit. If this acts as short circuit, if this is going to act as short circuit, you will find here, okay, you will find here this current whatever is there will go through this path, and the capacitor, if it has any charge, it has to discharge. The capacitor, if it has any charge, it has to discharge, because this is a low resistance path. So capacitor will not charge now. It will be in discharging mode if it has any charge. Okay, and this source current also will not enter into capacitor. It will go through this short circuit path only. Okay, this is the point you need to observe here. So this is how you will be observing this point. Now at this situation, okay, carefully observe. What will happen is that, because capacitor voltage is 0, carefully observe. This is the turning point now. How to understand? The capacitor voltage now it is 0. Now VC will be equal to 0 because it is not charging. So then I will have here 0. Please observe the negative terminal what you have for this op amp, because of the power supply it is fixed to 6 volts and this plus is at 0. So consider plus as reference and this minus as, okay, as the input. Now example, till now how we have studied, let us stick to that point only, even though it is observed here reverse. Now, so what I understand is input is at 6 and reference is at 0. Input is greater than reference. If input is greater than reference, then the output should be 0. So this output is 0. And at this situation you check. So the output of this comparator is 0. Now at this situation you check. You did not give any trigger. Okay. Now please, there is a point everyone should note. At this pin number 2, okay, you don't find any connection, which they don't show, because this is an integrated circuit. Okay, they show the minimal components in the circuit to understand easily. So what happens is, there will be an internal connection from VCC to this pin number 2. Okay, all of you are repeat. There will be an internal connection from this pin number 2. Okay, pin number VCC to the pin number 2. Due to that internal connection, this voltage will be maintained greater than 3 volts. Greater than 3 volts. Say, okay, say this point has 5 volts. Okay, say this point has 5 volts. Okay, now say here, say it is 5 volts. Now say it is 5 volts. So you should understand, it will not be exactly 5, it will be definitely greater than the voltage at this point. Okay, internally that will be maintained through this path. Okay, automatic adjustment will be there. Why? Because every time there is no rule that I will put here 9 and every time there is no rule that I will have here 3. What the point is, you will always be maintaining internally. Okay, now this point greater than this. Okay, now that is the reason in textbook they try to mention very clearly the trigger voltage should be applied less than 1/3 VCC. Why they mention? Because internally already there is a connection. Okay, whatever may be the voltage you give, okay, it should become less than 1/3 VCC. So they have pre-calculated it and put it. Okay, it is here 5 volts example I have taken. So the voltage, now this is the status I have. Now because internally there is a connection, at this situation I am not applying trigger. Remember, internal voltage which is there, that is at 5 volts. Okay, now input is greater than reference. Okay, input greater than reference, output should be 0. So this circuit output is also at 0. Now if S is 0, R is 0, you will have Qn bar. It means Q is 1 and Qn bar is 0. It means circuit remains in same state. It means you should understand from this point here that what you have reset, that is only going to continue, because you did not give any trigger for a monostable multivibrator. There is no change. It is in stable state. Okay, it is in stable state. At this situation, in order to find the operation of the monostable multivibrator, let us give trigger. Okay, let us try to give here trigger. So if you give trigger here, okay, if you give trigger here, now the trigger voltage must be applied like this. All of you carefully see. Okay, less than Vt should be less than 1/3 VCC. You should apply a voltage less than 1/3 VCC. Say because of the trigger voltage what you have given, this 5 volts has now reduced to 2 volts. Okay, now say that 5 volts has reduced to 2 volts. Because of trigger, this pin number 2 voltage has come down to 2. Now what will happen? This input is less than 3 volts. Okay, this input is less than 3 volts. So now the moment you apply trigger, as input is now less than 3 volts, immediately the output of the circuit will change to 1. Because V input less than V reference, output is 1. Immediately this will change to 1. But what about this status? Because this transistor is on, capacitor is still at 0 only. That is the reason this will remain 0 and this will remain 6 2/3 fixed. So this output also continues. Still it is in 0 only. There is no change. Okay, because capacitor did not change, there is no change. Okay, this is fixed. Capacitor has to change. Capacitor did not change. So this is also 0. It means when you have S0R1, you can see here S0R1, then Q becomes 0 and R becomes, okay, Q bar becomes 1. Observe carefully. This is the point. Okay, this is a twist you have. So when S is equal to 0, same state it is remaining. But R has changed. R has changed to 1. Okay, because R has become 1, then Q becomes 0 and Q bar becomes 1. Now observe carefully. The output has changed its reset value. It has changed to 0 and this has changed to 1. So the output of the circuit is visible like this. Okay, it is visible like this. Now it has changed to some high voltage value. Okay, some voltage value it has changed. You can say plus V sat. Now the question is how long it will be here in this state. Now carefully observe at this situation. Now because this Q has become now 0, observe carefully. Q has become 0. The transistor here it is 0. Then this will be off. You can see, everybody can see this point. Now because this is at 0 and this is here at 8 volts say, then this is at 0. 0 minus 0 is reverse bias. And 0 minus 8 is minus 8. 0 minus 8. So the transistor is now going to act as open circuit. Okay, it is going to act as open circuit. So the transistor will function as open circuit. When the transistor is not taking current, okay, it is not providing low resistance path. Now what happens? Carefully observe everybody. Now the capacitor gets opportunity to charge. So capacitor gets charging current. Okay, the capacitor starts charging. Okay, when capacitor starts charging, its voltage will increase. Okay, its voltage will increase. So I'll have here the capacitor voltage now 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, it will start increasing. Okay, now for all voltages whatever it is increasing, here this voltage pin number 6 will change its voltage 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. For all these voltages 1, 2, 3, 4, 5, input is at 6 and reference is at 1, 2, 3, 4, 5, which is changing. Okay, now all these values are, input is greater than for all these for all these values of reference. Therefore if input is greater than reference, output remains in 0. So this remains in 0, right? But what you need to understand here is that this trigger is applied for short interval of time. Okay, everybody carefully see. Trigger is applied for short interval of time. Due to that reason, once trigger comes to normal voltage, immediately this will change to 5 volts. Okay, because input is now is greater than reference, this 1 will change to 0. Okay, this will remain here in 0 only, but this will come to 0 to 1, and from 1 it will again change to 0. When S and Q are 0, 0 and 0, you will get previous output. What is previous output? 0 and 1 is previous. This only will continue. It means there is no change in the circuit. Okay. Now at this situation, capacitor is charging. When you are looking at this point, capacitor is charging, and capacitor voltage has come to now 6.1. Carefully observe, capacitor voltage has come to 6.1. So when the capacitor voltage has come to 6.1 volt, now here it is 6.1 volt. Now you can see that input is less than reference. Okay, input is less than reference. When the input is less than reference, immediately output has to change. Input is less than plus Vsat. That is, S becomes 1. Okay, but R remains 0 only. Why? Because internal voltage, once again it will come back to this point. And that is, now S is 1 and R is 0. Please see here, S1 and R0, you get output Q1 and this 0. So now this output has changed once again 1, and this has changed to 0. It means circuit returns to stable state. Circuit returns to stable state. So this is how you get the output. Now this is nothing but a pulse. So this pulse, what you are having, is given with the same time period here. Once again, what we have studied, okay, like this. So pulse time period, pulse width can be adjusted based on the resistor and capacitor value. Okay, so this is the functionality of the circuit what you have. Okay, now this is about simplified timer functioning as monostable multivibrator. And remember that always trigger pulse width should be less than the pulse width of the circuit. That is for sure, you need to get it. Copy this part. Quickly copy this. Now we'll look a stable multivibrator with a 555 timer. Quick. Now I am erasing this part. Now see here, the pulse width of this circuit, here we have to calculate T. So here also you use the same formula. Now Vc equal to V final plus, okay, V initial minus V final, okay, into e power minus t by RC. So there is nothing else here. Now the point here is, what is V final? Okay, that is capacitor voltage. V final value, capacitor will charge up to certain value, okay, and initial voltage what you have charged for the capacitor, it is 0. Okay, so now initial voltage of the capacitor is considered 0. Then I am going to get this as, okay, Vf minus Vf into e power minus t by RC. Okay, because Vi equal to 0, initial voltage of capacitor is 0. So take Vf common, I am going to get 1 minus e power minus t by RC. Okay, this is here Vc, but the capacitor will charge maximum up to what voltage? The reference voltage which is there. So this is 2/3 VCC. Capacitor will charge maximum up to 2/3 VCC. 2/3 VCC equal to V final is also VCC. 1 minus e power minus t by RC. Okay, you are going to get, cancel these two values and send this one this side, 2 pi minus 1, okay, is equal to minus e power minus t by RC. Okay, this is what I am going to get, or better write this one like this. Send this one this side, okay, and send this part this side. Then you are going to get here 3 minus 2. 1 by 3 is equal to e power minus t by RC. Okay, take log. Okay, take log. Then I am going to get e power minus t by rc is equal to, okay, log 1 by 3. Okay, now this I am going to get minus t by rc is equal to log 1 by 3 is nothing but, okay, minus ln 3, because log 1 is 0 here. Okay, so cancel these two functions. So t is equal to, now cancel minus here, t is equal to log 3 value here you are supposed to get, somewhere you will get this as 1.1 rc. So please observe here, okay, this point time period of this circuit is different from the op-amp circuit what you have taken. There just now we have seen for op-amp the pulse time period is obtained as 0.69 rc, but here you are getting, okay, t is equal to 1.1 rc. Okay, that is what it is. So don't consider this as constant functions. Based on the circuit existence and components connected, we get this value. Here for monostable, I repeat, for monostable you will get t is equal to 1.1 rc. In the previous circuit you got monostable 0.69 rc. So you should understand that based on circuit design we try to get the time period values, not they are fixed. Okay, fine. Now I am erasing this output part. Now let us try to see here the stable multivibrator, okay, circuit. So in stable multivibrator circuit here, because stable multivibrator circuit is a oscillator circuit, for oscillator we don't give inputs. Okay, so the output of the circuit has got no stable state. Or the stable multivibrator means it has no stable state. The output will be toggling between plus V side minus V side continuously. So you can understand here that a square wave will be generated by the stable multivibrator. So how that square wave is generated, let us try to see here this point. Now for that there is a small change in the circuit external terminals. So how, let us try to connect here this change, how it acts. Because there is no input, one should understand here the circuit will be connected like this. In monostable, pin number 6 and pin number 7 are connected together. Now here pin number 6 and pin number 2 will be connected together, okay, to the capacitor here, because trigger will not be given in a stable multivibrator. So here you can see now in this case, okay, one resistor will be connected, name it here R1, and one resistor will be connected here, name it here R2, okay, like this. So this is here a stable multivibrator circuit. Now all of you see a stable, I am writing it here, a stable multivibrator circuit. Okay, so this is a stable multivibrator circuit. Okay, fine. Now I am erasing this part. Now at this situation, same kind of operations, there is no change. Initially set these values such that this is 1 and this is 0. Okay, set the outputs here, this is 1 and this is 0. Then obviously the output what you are observing here for this circuit, okay, you are going to get it like this. Okay, output of this circuit. Initially output of the circuit is maintained 0. So you can observe here the output is maintained 0. Okay, fine. By resetting these values. And now once what happens at this situation is, okay, everybody try to understand here. Okay, initially when it is set to here 0, okay, now this part of the capacitor you can see when that is 1, okay, you have to take charged capacitor initially. Okay, take charged capacitor initially here. First you have to charge, then only the circuit will start. Because in oscillator we don't give input and we get output. Okay, that is the point. This is the oscillator circuit now. We don't give input and we try to get the output. If that is the case, okay, the capacitor, okay, must be given. Initial start must be there in oscillator. For that we need to take here charger capacitor. If you take charger capacitor, already the capacitor is charged. Okay, because you have reset the value to 1 and 0. Now what happens is, now the capacitor gets opportunity like this. Okay, initially it has charged, so it is there like this, but it is connected to the transistor here, which is going to work as a switch, because the transistor as here, that is Q is equal to 1. Okay, transistor is on. So what happens to the capacitor now? It has to discharge through this resistor. Okay, it has to discharge through this resistor R2 like this. And the supply source what you have from VCC, now this also will discharge like this. Why? Because this is low resistance path. Now this here has got initial value. VC of 0, it has got some initial value. So let me put it like this. V0 of C. What do you mean by V0 of C? Means initial charge is there in the capacitor. Okay, initial charge is there in the capacitor. Because initial charge is there in the capacitor, now it starts discharging. When it is discharging, the capacitor voltage will reduce. Now, all of you carefully observe, the capacitor voltage will reduce. Okay, as this is fixed now, once again 9 volts, 3 volts here, 6 volts here, capacitor voltage will reduce. Okay, when its voltage is reducing, say capacitor initially is charged to 5 volts, put for example 5 volts, capacitor started discharging. When the capacitor started discharging, its voltage will reduce and come down to 2 volts. So initial VC is equal to 5 volts, say capacitor is charged to 5 volts, say, then this voltage is going to be reduced. So as this voltage goes to reduce here to 2 volts, now input is less than reference. If input is less than reference, then the output of this circuit, which was initially 0 and 0, here this will change to 1, but this remains as it is 0, because still this did not change. Okay, now here this has changed to 1. When S is 0 and R is 1, the output of this circuit is going to change like this. Q remains 0 and this becomes here 1. Okay, now obviously this changes to 1 and this is 1. Now you can see here the output of the circuit is going to change from this point like this. Okay, like this. So you are going to get it here like this. Now the question is how long it will remain like this. Okay, how long it will remain in this position. Okay, now try to see here, as long as this is working with this condition, it will remain like this. Now capacitor discharge and it has come down to 0. Okay, so it is coming, it want to come down to 0. But what happens suddenly now? When this Q has become 0, transistor has become open circuit. This is now off. When Q is equal to 0, Q1 has changed to 0, transistor has changed to off. This is open. Now capacitor will not discharge. And this source current also will not come this side. Now capacitor starts charging. Okay, capacitor starts charging. Observe carefully. Okay, the capacitor, carefully observe. When it is discharging initially, okay, the time period will be 0.69 R2C. And when it is charging, now it is 0.69 R1 plus R2C, because 2 resistors are there. Okay, while charging, 2 resistors are working here. Okay, so it works like this. Okay, like this. It is charging in this manner. So now capacitor starts charging. How capacitor will charge? Now once again this voltage will go greater than this. Carefully see here. Input will go greater than this. So capacitor once again charges okay, from 2 volts again it will return back 3, 4, 5 like that. It say it is 5. Now input is greater than reference or 4. Okay, immediately this will change to 0. When this is 0, this is 0. When inputs of flip-flop are 0, the output is not going to change. It continues in previous state. It continues in previous state. So you can observe here like this. So it is going to continue in previous state. Now capacitor will not remain here. It is going to charge like this. 2, 3, 4, 5, 6, and it becomes 6.1. Okay, it becomes 6.1. When the capacitor voltage becomes 6.1, pin number 6 voltage will become 6.1. Now input becomes less than reference. Input becomes less than reference. If input is less than reference, then output should be here at plus V sat. So this output becomes 1. So this is at 1 and this is at 0. When S is 1 and R is 0, okay, S is 1 and R is 0, then Q becomes here 1 and Q bar becomes 0. So you can see here the output has shifted from this point to this point. like this. Now because this is a stable multivibrator, it is not going to stop here. When this becomes here again 0, carefully observe. When this becomes here again 0 here, okay, at this situation, now I have turned here this to 0 and this has turned to 0 and this has turned to 1. You can observe here this has turned to 1. Once again the transistor is on. Once the transistor is on, now capacitor cannot charge further. It has to discharge. So you can observe here again the capacitor is going to discharge. Okay, again the capacitor is going to discharge. Just now capacitor has charged up to 6.1. So it want to charge more, but it will not get opportunity because the transistor is acting as short circuit and it will return back towards low voltage now. So it comes back now once again. So again capacitor voltage falls down. Everybody carefully observe this. It falls down to 6, 5, 4, 3, 2. Okay, the moment it becomes 2 here, okay, when capacitor is discharging, at that situation 2 is less than 3. When input is less than reference, now this once again becomes 1 and this remains here at 0. This has changed. Okay, so 0 and 1. So when 0 and 1 are there, then Q becomes 0 and Q bar becomes 1. Once again this has changed. Observe, this becomes 0 and this becomes here 1. Once again you are going to get the pulse like this. Once again you are going to get the pulse. So this will remain here for short interval and you are going to get the output. So the entire circuit, the logic of this circuit has to be understood. This entire operation has to be understood in 2 lines. You should not take more than 2 lines. Please try to see here, everybody. So the entire operation, instead of understanding all these things, you can understand like this. When, carefully observe this table, when, okay, that is capacitor voltage is greater than 2/3 VCC, greater than 2/3 VCC. Now, when the capacitor voltage is greater than 2/3 VCC, then the output of circuit will be, okay, output of circuit will be there here 0 because 2/3 VCC, this becomes 6.1, input is less than reference, S becomes 1. Okay, then S is 1, Q becomes 1 and this becomes 0. And here when input, okay, capacitor voltage is less than 1/3 VCC, okay, less than 1/3 VCC, then output becomes 1. So this is the only simple table. The entire explanation what we have studied can be understood only by this. If you remember this logic, in 1 second you can answer this entire operation. Just remember this point. Okay, it is the capacitor voltage which takes entire control over here. So the entire explanation can be understood with single table. Now let us take break, okay, and come back. Wave continuously like this, he'll ask you frequency. You need to calculate time period. So time period of this circuit is calculated like this. TD plus TC you need to calculate. So based on time period you will try to get the what you call the function here TD plus TC. I'll explain this. Okay, let me clear the doubts. So based on that, once you get time period you will get frequency. So he'll ask you what is the frequency of the oscillator. Okay, then you need to calculate time period and put the answer. Next. Ashutosh from Billai. Sir, as per the diagram you gave for monostable 741 structure at non-inverting input where diode D2 was connected, I connected small value of capacitor before diode and in series with it. Now I trigger it. As a result, the width of the output has now, irrespective response of how long I am holding the input trigger, okay, trigger switch to on. I mean to output goes low after deciding the value of T no matter I hold the switch or not. Okay, now to trigger again I have to release the switch, then have to press it again now. Why is it so happening? Please comment. So it's very good you have done the experiment. Okay, so the point here is that as long as you are giving the trigger, okay, the comparator output what you are getting it, okay, it will not change. Capacitor will be charging. you have to stop the capacitor charging, then only it will return back to original state. Okay, because capacitor is still charging, that is the reason output will be holding to the same value. Okay, so when you are pressing it, so if you remove the switch, okay, if you remove your hand from the switch, then what trigger? That is what I mean trigger. Then the capacitor will stop charging there. Okay, why? Because that will not stop immediately. It will stop after a long time. That is the reason you are getting the result like that, because you have to consider charging time of capacitor towards minus VC, towards minus V reference. Okay, and also you should consider the capacitor return back from minus V reference to 0. Why you are getting the output? Because of that reason. Okay, that is the answer for your question. Next, the T from Gujarat. What is the difference between the two circuits of multivibrator? We have studied one 555 timer and previous one, which one is more major? 555 timer is efficient. That is what I have given the introduction earlier. Okay, so you can understand that. Why? Because here the accuracy levels are more. This is specially designed for the what you call application, because if you use 741, offset conditions will be more. But here this op amp what you use here is not 741. It is designed exclusive comparator. Okay, but anyhow comparator principle is always same. Okay, so that is the reason you will have less components, so less complexity. Because of that, more efficiency can be improved from this circuit. That is what you get. Sir, what is one shot mode, free running mode, IC 555 timer? One shot means only one pulse. That is nothing but monostable multivibrator, what we have seen before this. And free running mode IC is nothing but this is a stable multivibrator. That is what is a stable multivibrator. Rohit from Mumbai. This is the answer for your question. One shot means monostable multivibrator, and what do you call free running means a stable multivibrator. Now let us complete here this part of time period. Okay, so you are supposed to get here the time period like this. As I have written here, TD is plus TC. So you try to take here I am writing at the top. So T is equal to TD plus TC. So this you are going to get it as TD is given as 0.69 RC, okay, R2C plus 0.69, okay, R1 plus R2C. So you are going to get, so the total time period will be 0.69 into R1 plus 2R2C. Okay, this is the time period. And frequency of oscillations, because it is a stable multivibrator, then frequency F is equal to 1 by T. So this is the formula for time period of the pulse and as well as frequency of oscillations. So you will get questions on this topic. Okay, you will get questions on this topic based on these points. That is T is equal to 0.69 RC. Okay, 1 plus R1 plus R2, 2R2 into C. Okay, based on the values of this adjustment. And remember to get a square wave. Okay, all of you be careful here. This is very important. Okay, if R1 is, okay, R1 and R2 you need to compare. By adjusting the value of R1 and R2, you will get equality part. Why? Because the charging time is different from discharging time. You can see here. Here you will get a square. R2C divided by, okay, 0.69 R1 plus R2C. R1 plus R2, okay, total time period is 2R2. Okay, 2R2C. So cancel this function, okay, into 100. So I am going to get here this as R2 divided by R1 plus 2R2. Okay, into 100. So this is percentage of duty cycle I have. So this is what we call duty cycle. This is also important. He will ask you question on this. A duty cycle is there only for a stable multivibrator. Okay, not for monostable, because this is an oscillator here. Okay. Now what do you mean by duty cycle? In sense, the capacitor, how much charging period and how much discharging period you have to consider. That is the reason you are supposed to take it like this. Okay. So this is what we have here in the case of 555 timer. Okay, working as a stable and monostable multivibrator circuits. Okay, this is the point you need to remember here. Fine. So we conclude the class here. in the next class. Okay, we'll try to proceed with the next topic. Now